Hello everyone, this is Sayim from the University of Southern California. I was a postdoc at Weill Cornell Medicine during the submission of this abstract. In this talk, I will be happy to summarize the findings of our research work called In-silico shimming performance of a bore-sized 2D UHF volume coil for different anatomies at 7 Tesla. Here are the financial supports that we have received during this work. As is well known by the society, UHF promises improved signal-to-noise ratio, but this comes at the cost of higher specific absorption rate and lower transmit field homogeneity due to shorter electromagnetic wavelength. One critical barrier for dissemination of the UHF is that there are no vendor-provided bore-mounted body coils. With that being said, there are local coil solutions for specific anatomies, which are driven by PTX systems. There are only a couple of attempts to address the bore-mounted UHF coil problem to date. We hypothesize that the 2D e-HPL architecture is a promising candidate for a bore-mounted UHF coil since it facilitates the tailoring of B1 field in both the longitudinal and azimuthal directions. In this work, we will briefly demonstrate the in-silico shimming capability of a 2D e-HPL coil. Let me recall the working principle of the 2D e-HPL coil first. Similar to birdcage geometry, we start with an inductively coupled loops, which can be driven as a PTX system. We then extend this coil to 2D by cascading additional rows, with inductive coupling for all elements. The eigenvalue problem for this two-dimensional ladder network can be solved both analytically and numerically and yields a dispersion relation and current amplitude distribution as shown here. More details can be seen in our previous publications. The 1-1 mode yields the most homogeneous B1 distribution inside the coil and is therefore the most suitable for imaging. In this case, the 1-1 mode appears at the high end of the dispersion, and thus this design is high-pass in nature. This architecture can be operated with simple quadrature excitation, but also allows for PTX. Note that a key feature in this design is that the operating frequency depends mostly on the single element resonant frequency and the mutual coupling between the consecutive elements, thus supporting high field operation. To compare the performances, we also designed in-silico TEM and birdcage coils with the given dimensions. Numerical results of phantom simulations with Sim4Life showed that the proposed structure may have better B1 plus homogeneity, lower specific absorption rate, and better SAR efficiency compared to the similar sized TEM and high-pass birdcage coils. As you can see, about 45% reduction in maximum SAR and 15% improvement in SAR efficiency is observed. In addition to phantom simulations, in-silico body model characterizations also verifies these with a similar SAR decrease and SAR efficiency improvement. As a further test of operating characteristics, we repeated the previous simulations with different anatomies, this time by using RF shimming. On the top row, you can see the head-sized coil results. Whole brain results are given in figure B, and cerebellum-only region RF shimming results are given in figure C. Similarly, for the body-sized coils, you can see the RF shimming results for heart in figure E and for prostate in figure G. They are all below or similar to previously reported values. A successful bore-mounted body coil should operate in large field of views as well. We ran RF shimming for the whole chest region of an ELLA body model. We have found that the coefficient of variation can be as low as 11% for in-plane and about 37% for the whole chest region. In conclusion, we verified that inductively coupled passive elements can be used to create larger coils. We report lower SAR and better B1 plus uniformity compared to conventional volume coil architectures. We showed that 2D design allows for longer coils even at UHF. Last but not the least, a bore-mounted structure allows for RF shimming for different anatomies such as brain, heart, and prostate. This structure avoids the delicate array placement of PTX-based surface arrays. Thank you for your attention.